First let me thank Rick and Tim for the opportunity to contribute to the symposium on imaging mass spectrometry, and today I will discuss the aspects of imaging mass spectrometry in pharmaceutical applications and how imaging mass spectrometry assists in developing new medicines. In drug discovery and development, the challenge is to get an in-depth understanding of the final, ultimately in vivo drug behavior, which is achieved with detailed ADME studies, which are absorption, distribution, metabolism, elimination, excretion, and toxicology. And while the gold standard for analyzing these samples is liquid chromatography, LC-MS, when you have biological fluids such as urine, blood, and CSF, you just perform a dilute and shoot or proteins precipitation or solid phase extraction, and you can then analyze it by LC-MS. However, when you have localized tissue samples, you need to homogenize these samples, analyze it by LC-MS, but you have the loss of spatial information. Especially when you perform toxicology studies, the spatial profile of the drug and metabolites or endogenous compounds can potentially provide information on the mechanism of toxicity, which has relevance to clinical safety. For intact tissue analysis, we have quite a large analytical toolkit, which is nuclear magnetic resonance, quantitative whole body autoradiography, CAT or positron emission tomography. However, the possible limitations are sensitivity, spatial resolution, and the need to synthesize isotopically labeled material. For example, for QWBA, you need to synthesize your compound 14C labeled, versus if you do positron emission tomography, it's 11 carbon labeled. And especially in the early stages of drug discovery, there is no time and also no funding to synthesize these quite complex compounds using these isotopes. So the technology that is applied here, tissue imaging by mass spectrometry, has no requirement for isotopically labeled material, and therefore is very attractive to look at intact tissue. It has no requirement for isotopically labeled material. However, when there is isotopically labeled material in the tissue, the mass spectrometer can analyze it too. The basic workflow of MSI is that the tissue are sectioned in the microtome or cryostat, frozen, and are placed on a sample carrier. Then the ions are generated at each pixel, which gives us the X and Y coordinates. The ions are detected by mass spec, affording an array of mass spectra, and then data are processed into ion maps, which can be or we just learned, three-dimensional. And Professor Caprioli some time ago termed the phrase, we are painting molecular pictures, and I actually found this Andy Warhol-like display of a brain section by Alexandrov, where here you have the visual picture, but these are images made by mass spectrometry. And the different colors represent different ions detected in the brain. But we are beyond pretty pictures, so what does it actually mean? What are we detecting? So in drug discovery and development, there are basically three applications that we use MSI for. We have the active pharmaceutical ingredient, API, and we are looking what is the body doing to it. So we have pharmacokinetics, which means is the target engagement, is actually the compound reaching the tumor, is it reaching the target? Then what is the target distribution? You know, are there specific regions where it's localized, where it's not reaching? And of course, does the drug form metabolites, which sometimes can be the actually more active compound, and sometimes it's the reason for toxicity. Then also to support histology and pathology, basically what is the drug doing to the body? So are there any changes in the endogenous metabolites in the target tissue? And then various forms of omics, you know, the comparative analysis of the endogenous metabolites in normal versus non-normal, which could be diseased or dosed tissue. So looking at MSI and drug discovery and development, you know, the days are over where you just see an instrument and you buy it and you put it in your lab and you try to make it work. So, you know, what is the return on investment? So when we bring MSI into the pharmaceutical industry, the first question is, what will be the impact? What what will we get when we bring this technology in? What is the cost and what is the ease of use? What analytes can we see? What is the resolution? What is the speed and throughput? How difficult is it to generate the samples or even prepare the samples? What is the data quality? Will we have qualitative data, quantitative data? How difficult is the data processing? So today I will talk about the following MSI technology as they apply to drug discovery and development, and with a specific emphasis on the third one, which is MALDI. But let's start at the top. So desorption electrospray ionization, laser ablation, inductively coupled plasma MS, matrix-assisted laser desorption, MALDI, nanostructure, initiator mass spec, secondary ion MS, surface sampling techniques, and then although it's not an imaging technique, I also want to touch upon laser capture microdissection. To start with DESI MS, Professor Cooks, who is here in the audience, is the inventor of this technique where you have the tissue placed on a carrier and you have an electrospray basically ablating the ions of interest that are then detected by the mass spectrometer, and you move these stage to get your X and Y positions. Here's an example from the literature where on the left upper corner there's an image of a lung tissue, B displays the image of a drug, C displays the image of a drug metabolite, and D is actually the MS image of an endogenous lipid. And the reason the authors did the experiment as described is that they could actually normalize the drug and the metabolite against the endogenous lipid and were able to obtain semi-quantitative data that they were able to confirm by traditional LC-MS. In summary of DESI, it's for the analysis of organic compounds, small molecules, lipids, peptides, and proteins. No sample preparation for mass spec analysis. Multiple charge state are observed, which is important for peptides and proteins. The spatial resolution is probably at the moment above 100 microns, but I'm very careful to make a statement here because it's really evolving. There's nano DESI coming out, and probably after Pittcon there are different numbers. And I think where we can use it is for whole body MSI, where you have a rat that is sectioned and you have to quickly compare the brain to the intestines. This is the perfect technology to get data quick. Moving on to ICPMS, here you have a laser basically liberating the analytes from the tissue, which are then with an argon carrier inert gas carried into the plasma source and then are detected by mass spectrometry. And here's a very intriguing example that on the top you have an image of a brain with A beta peptides, and they are visualized with an antibody. And here's a more detailed picture. This antibody was labeled with the isotope 60 nickel, which is then detected by ICPMS, which illustrates where the antibody is linked to the A beta peptides. So now the question is, we already saw it up here, why do we have to do ICPMS to find the antibody? Alzheimer's disease is also, in theory, associated with abnormal metal deposits. So we might have the isotope 60 nickel, but you can then image for copper, for aluminum, and all the other metals and see if there is a correlation with the A beta deposits, with the A beta peptide deposits and these metals, and try to do some further research on Alzheimer's. ICPMS is for the analysis of elements. Again, no sample preparation for mass spec analysis. The spatial resolution is less than 100 microns. And just to give you an idea, we typically say 10 microns is the width of a cell, so this is clearly larger than cells. It is being used for neurodegenerative diseases, for brain analysis, for oncology, where you have metal-containing therapeutics like cisplatin, metallomics, where you try to distinguish disease state versus healthy based on metals. And I think this is intriguing. This will be used more often, is the indirect measurement via metal-labeled antibodies. Moving on to MALDI MS. here is just a schematic of a MALDI-MS experiment. Up here, this is a spleen which is then cryosectioned and placed on a glass slide. Then you apply the MALDI matrix, and then you have the rastering of the laser across the tissue, and you have spot-specific mass spec data, which then allows you post-data acquisition processing to achieve mass-specific ion images. The role of the MALDI matrix here, and this is a challenging part for utilizing MALDI MSI, is that up here is a schematic of a tissue on a glass microscope slide, and you can see that the analytes are distributed throughout the tissue. They are not necessarily on top of the tissue. And when I started doing MALDI MSI early on in collaboration with Professor Joost, I was kind of disappointed how weak that laser is. You know, you think about, you get a laser in your lab and you think of all the cool experiments you can do. These lasers are actually very weak. They don't even burn through a paper. They only touch the surface of the tissue. So you have to bring your analytes to the surface of the tissue, and you achieve this by MALDI matrix application, where you apply the MALDI matrix in solution a couple of times, 10 to 15 times, and what you do is you basically get an extraction of the analytes to the surface of the tissue where you have co-crystallization with the MALDI matrix. And then the laser itself ionizes the MALDI matrix and co-ionizes the analytes. So the challenge is the homogeneous application and to get the analytes extracted and also to avoid lateral dislocation of the analytes. So here are some examples from my lab is where we had to analyze a tissue for API, and the workflow that we implemented is that first, when we look at a tissue, we always make a map of mass to charge 184 because this is indicative of lipids. And with the application of MALDI matrix, there's kind of, you know, the good day factor to it. Sometimes it just doesn't work and you don't know why. And if the tissue is not displayed correctly, that sample will not be used for data processing. So this is for us a technical marker that if 184, you know, related to the lipids is not a nice picture, we basically don't take the sample. We also look at the marker of the MALDI matrix itself. We don't want to see a discrimination. We are using, you know, either commercially available sprayers to apply MALDI matrix or even an airbrush, and you know, it might be that sometimes you just don't get that homogeneous application. So if these two technical controls pass, then we look at the tissue, and here we can see the API and tissue utilizing MSMS on an ion trap. We see a homogeneous distribution, and then we also go to MS to the third to confirm that it's the analyte of interest. Your data are only as good as your control, so what we have here is a control tissue. Again, we image 184, we image the 273, again the marker ions, the technical controls pass, and then doing MS to the second and MS to the third to look at the data. Why are we using MS, these higher stages MS? So on the left side, here's the API in tissue, and this is MS full scan, and you can see 184 and 273, and here are the lipids. And then, you know, unfortunately I cannot tell you the transitions, but doing MSMS, you see you still get, compared to a blank standard on a metal carrier, you still see a difference in the MSMS full scan spectrum. Only when going to MS to the third, we feel that we actually have 100% confirmation of the analyte of interest. So we have the advantage of a MALDI ion trap in our lab, so we can do MS to the third, and actually we have done experiments up to MS to the seventh on tissue. And so the specificity that is necessary to make a positive confirmation, and you have to think about some of these data may go to regulatory affairs, so you really need to confirm your analyte, and there's no interference from an endogenous component. So MS to the third or high resolution accurate mass gives us the specificity. Another example from the lab is where we had an animal that was dosed with a formulation containing vitamin E TBGS, and when I looked for the analyte, and again the advantage of an ion trap, you you acquire all the data, I found that there are areas where there was PEG, in my opinion, PEG 1500 was accumulating, and I went back to the formulation chemist and I said, I don't see the analyte of interest, but I see the PEG. And he said, no, I'm not dosing with PEG. We are using vitamin E TPGS. And looking into the literature, vitamin E TPGS is actually an ester with PEG 1000. So, you know, whatever they do, they cannot hide. We will find it. Another example where we had an assessment of phototoxicity using ocular distribution. Here we have a QWBA where this is a compound in development. So there was, the path forward was to synthesize a 14C labeled API which was dosed to animals, and there was a concern about phototoxicity, and doing QWBA, this is a cut of an eye. You can see the compound accumulates in the retina and uveal tract, and it appears there's nothing in the cornea. The problem is with the 14C label, it depends where you put it, and if there are some metabolites circulating or metabolites forming, they might or might not have the 14C label. So it might be that there might be a metabolite without the label. So we received these samples, and again, doing our procedure is, again, we look for the marker iron 184, so we get the lipids, so we are able to image the whole eye. So we are not discriminating an area. And then looking at the API and metabolites, you know, when a compound is in development, you know what metabolites to look for. You can see that it accumulated in the retina and uveal tract, but the cornea is actually compound and metabolite free. So this was actually very important for this compound to progress and advance into the clinic. MALDI-MS is also used to analyze lipids in the brain, where you can have certain areas where these specific lipids accumulate, and this was done by Garrett and Joost here. And then we also have some an example where you have distribution of proteins in the brain, and here the problem is that you might detect these proteins, but it's very important to do the analyte identification and subsequent validation. So in summary, the MALDI is used for the analysis of organic compounds, small molecules, lipids, peptides, proteins. There is a sample preparation for mass spec analysis, the matrix application, and having it done for many, many years, there's still always, you know, the butterflies in the stomach whether you do it right or not. There are some deposition techniques such as spraying, printing, sublimation, and I'm sure there are coming more. The nice thing is it allows you to choose the matrix. The matrix actually can enhance the detection of certain analytes. And I think also we have now to look into nanomaterial. There are some articles coming out where nanomaterial with easier application are coming forward. There's a single state, charge state observed with MALDI-MS, and the spatial resolution is now less than 100 microns, and the sample throughput is clearly dependent on resolution and laser type. These examples that I showed of these tissues, even the eye itself, one analysis is 8 hours. So if you get 2 analyses done in a night, that's a good data set. Moving forward to NIMS, here's a schematic of an application of or utilizing NIMS, which is porous silicon surface coated with a Teflon-like polymer. And what it is that this research group by Professor Sustek, instead of putting the MALDI matrix on top of the tissue, they actually put the MALDI matrix on the glass or on the carrier itself. And by applying or by putting down a very small tissue section, you actually have the laser liberating the nanomaterial, and then the nanomaterial moves into the mass spectrometer, carrying the analyte of interest with it. These are early times for NIMS, but here there's already an example where we have an optical image of a lung tissue, and you have the MS image of the drug, which is clearly located in certain parts of the lung, versus the drug metabolite is distributed throughout. So I think this application shows the potential of nanomaterial. At the moment, it's being used for small molecules. Again, no sample preparation for mass spec analysis. spatial resolution dependent by the laser, of course, less than 100 microns. But there's extensive preparation of the sample carrier itself. But I think here nanotechnology moving forward will provide us with more sample carriers. Here's a schematic of a SIMS experiment where you have the primary ions from the ion cannon hitting the sample, and then you have the secondary ion extraction and detection by mass spectrometer. And here's an example where a boron-10 containing drug, again a non-natural isotope, a labeled drug was applied, and you can see that we are actually at cellular resolution with SIMS. It's used for the analysis of compounds. There is some fragmentation observed with SIMS, so it's more limiting SIMS to the analysis of elements and smaller molecules. Again, there is no sample preparation for mass spec analysis, and the spatial resolution is less than 10 microns. And the last imaging technique I would like to review is the surface sampling techniques, and I think they are behind because they don't have an acronym yet. So what you see here is, here's a tissue section of the brain, and what these authors are doing is it's basically a pipette tip that is moved to the tissue, and a liquid junction is performed, and the liquid is basically being moved up and down, and you have an extraction on the surface of the tissue. And of course the software allows you to move that sample drop up and down 2 times or 50 times, depending how much you put into the software. And the early data that was shown here is that if you have an optical image of a brain tissue, and then the drug itself is only in the periphery of the brain, versus the drug metabolite goes into the brain itself. So I basically should elaborate here. The pipette tip, after it has the liquid, is then turned and submitted to mass spec analysis. It's being used for small molecules. Again, there's no sample preparation. The spatial resolution is clearly more than 100 microns. It's more than like millimeters. But again, if you look for quick answers on a whole body, again, the question, is it in the brain? Is it in the intestines? Is it in the heart? Is it somewhere else? This is the technique where you get data with a quick turnaround. Moving on to laser capture microdissection. Here's a schematic where you have the tissue mounted on a carrier. You have the laser cutting out at the cellular level, of course larger if you would like to have so. And then the sample is extracted, and the nice thing now is that this can be moved into an Eppendorf vial and submitted to any standard LCMS or just mass spec analysis, or for that matter for any analysis. And the computers now will follow where these cells were extracted. So you actually make an image of the tissue, although you do not direct tissue imaging. And here's an example where this is a high-dose animal, an animal that was dosed at the highest level with a prodrug, and we had some areas where there was some it was dosed so high that there was some crystalline material here visible. And the question was, is it the prodrug or is it the drug itself? And doing MALDI imaging, we were able to confirm these areas as the drug. So the prodrug was liberated to the drug, so actually everything was as it should be. But since we had these samples, we performed laser capture microdissection in these areas. So these are crystalline-rich areas, and these are crystal-free areas, and just call them A and B. And then once we got these laser capture microdissection samples, which are literally in an Eppendorf tube, then we did just regular MALDI MS, and you can see that the intensity A compared to B, it's probably or about twice as much or higher concentration here when it's normalized to 202, and on the bottom you see a standard. So we used up about 1 microliter, and after that we could actually submit it to LCMS. And on top again, this is the LCMS trace, MSMS trace of an area from here, from A, and B from down here. So we have the high crystalline area and no crystal area. And since it's a high-dose animal, you always will find drugs at these levels. And here's the standard. But knowing how many cells, or estimating how many cells we extracted, and having a calibration curve, just doing regular LCMS, we were actually able to calculate the concentrations and to get it to 250 to 600 femtograms per cubic micron compared to 100 to 250 femtograms per cubic micron. So in summary, laser capture microdissection can be used for the analysis of organic compounds and elements, and there is no sample preparation for laser capture microdissection. And the nice thing again is that the laser capture microdissection samples can be processed to be qualitative and quantitatively analyzed by any technique. So these samples could have been submitted also to LI ICPMS, and the spatial information is maintained. So for us, actually, laser capture microdissection is considered an imaging technique. So now, after we went through these examples, so where is actually MSI standing in drug discovery and development? Cost and ease of use, it's not more expensive than a regular mass spectrometer, and it's as easy or as difficult as any mass spectrometer. I think it really gives us an answer on any analyte, on any resolution, using the array of techniques that I showed. Speed and throughput, we get a C grade here. We are not there. But if you look at the data that are acquired, I think it's worth doing it. The sample generation is not more difficult than doing histopathology. The sample preparation, most techniques don't have sample preparation with MALDI. You still have to work with it and try your best. I think the data quality is outstanding. The qualitative data is outstanding. The quantitative data and the data processing is still a little bit cumbersome, but people are working on it. And so far, on any samples that we received for imaging mass spectrometry, we had impact on the program. So there's clearly a return on investment for MSI in drug discovery and development. For the outlook, MSI provides ion maps, molecular pictures on metals and elements, on organic compounds, small molecules, lipids, peptides, proteins. It is an evolving technology. Just coming here to Pittcon, there was already an article on laser ablation, electrospray ionization MS, LAESI-MS, where again they claim there's no matrix preparation necessary. It's an evolving technology. All these samples that I showed were ex vivo samples, but there are now applications of imaging mass spectrometry to in vivo settings where surgeries are supported by mass spectrometry, for example, to establish tumor margins. It is clearly a complementary technology. It's not replacing anything. I showed some examples with QWBA and imaging mass spectrometry. The concerns and opportunities, in my lab, we have to verify and not detected with follow-up experiments. There are some analytes that will not work by imaging. We had some examples where we saw some protein binding and it would not extract, but it's a very easy test. You just take your sample, you put your drug of interest on top and analyze it an hour later, and if you cannot detect it, it just doesn't work. So there are some analytes where imaging doesn't work. There's some concern about data normalization across different tissue types. Can we compare the data from brain with intestines? Is the ionization efficiency the same, so that we need some better data normalization here? And then pharma is moving to biopharma. We are now having novel analytes. We have the modified proteins, the biotherapeutics, the pegylated proteins that we hope now will become medicines. How will we do the imaging on these analytes? And at the end, I would like to acknowledge the management and the peers and the collaborators, and would like to thank you for your attention and any questions or comments.